Perfect. So let's begin the session. So first of all, good evening, good morning, guten Tag, konnichiwa, everyone from different countries. So today we'll be starting with the paper by Google Research, and so a simple framework for contrastive learning for visual representation. In short, it's SimCLR, and presented by Shen Ting. And yeah, it was published by them. So I'll be presenting it and explaining what all they have come up with and the interesting findings. Okay, so let's begin. Okay, so my presentation would something look like this. So first I'll introduce the concept of self-supervised learning. What are the approaches? It's like generative, pretext task, contrastive learning. And then I would come to the main concept that they have introduced and the implementation detail and a couple of findings, which include the contrastive loss, data augmentation, projection head, batch size, and epochs. It's a bit broad topic, but if you have any questions, please write it down and then we'll clear it at the end. So what is self-supervised learning in the first place? So as you all may know, we have a lot of data right now on the internet, and even personal data people have. So the main problem with today with deep learning is one has to label, annotate the data manually, and this causes a lot of sometimes it's a manual task which becomes boring and can cause human errors, which is very natural. So what people have come up with, instead of having labeling the data, we just use the unlabeled data, train a pre-trained network unsupervisedly, and then use it for downstream application, which is like image classification, semantic segmentation, object detection. Okay, well, so one approach to do the self-supervised learning is a generative approach. So what we do is we have an image, and as you all may know, it's an autoencoder thing. So we have an image, we compress it, and again, reproduce the same image. And then we try to measure the loss from the output and the input image. So if you may see, if you are comparing the images in the actual space, it may become a very memory inefficient task. So instead of learning all the features and all the pixels, we can just have an high level features which are enough to distinguish different tasks in case of object recognition, for example. And also this task may be unnecessary of reducing the image again. So what people have come up with is a pretext task. So we solve a pretext task, we train a network, and then use the representation and the network for downstream applications. So people have come up with very interesting solutions. For example, solving a relative patch location. So for example, we have an image divided in multiple patches. So given one patch, the network is trained to predict another patch at another location. So for example, it is trained to predict, let's say 3. So multiple patches, it learns a representation, learns the weights, and then this network is used for downstream applications. So another is like rotating the image. So we put the image, rotate it, and ask the network, what is the rotation? So is it rotated 0 degree, 90 degree, 180 or 270? In this way, it would learn a representation without the without the data augmentation. And again, it's solving a jigsaw puzzle task. So all different formulations, different things, but the concept remains the same, to learn a representation. So now comes the contrastive learning. So what do you mean by contrastive learning? So as I mentioned earlier, instead of comparing the losses in the actual output space of the image, we just do it in the latent space. So latent space means reducing the dimensions of an image and then comparing it in that space. So a lot of methods are there. For example, MoCo, SimCLR, which we are discussing today, Beol and SWOT. So these two methods were more recent than SimCLR, and before that it was MoCo. So in Moco, I'll just give a small overview of it. So we have an image, which is a query image, and then we have some keys. So these keys are also some images, and it's a sort of memory bank, which is passed through a encoder, and then it's sort of a dictionary. So we have a lot of keys here, and then it is compared with the query. So the task of the network is to make the query similar to the queue. In that way, it would learn a representation, an encoder network, which would be used for downstream tasks. And this momentum encoder is a exponential moving average of this encoder. So next is this SimCLR we would be discussing in the couple of minutes. So I'm not explaining it right now. And then it's Beol. So this was a later one of the state-of-the-arts network, presented later than SimCLR, but I would just give you an overview of it. So in this, we use two networks, an online and a target network. Instead of having a negative negative sample, the image is compared with itself with another augmented view. So the aim of the network is to predict the image so that this latent space image is similar to the target image. And in this way, it would learn a network, and then this network would be used for downstream applications. Okay, so what is SimCLR? The concept, implementation, and the key findings. So as I introduced before, the main aim of contrastive learning is to maximize the agreement of representation under data transformation using contrastive loss in latent or feature space. So we have so we have an image, we put it through a different to data augmentation, put it through the encoder, CNN, and then we get a representation, which is again put through a projection head. We get a representation at the latent space, and then this representation or this image is compared with the another image in the data set, so that the image with the negative sample, the distance should be high. However, the distance between the different augmented views of the same image should be close. So then in this way, the base encoder network F and a projection head G are trained to maximize the agreement using contrastive loss. So after the training is complete, we throw away the projection head and use the encoder and the representation H for downstream tasks. And why do we throw this encoder F is something that they have come up with, which is one of the key findings of this paper, and we would be looking at in a short moment. Okay, so what was the implementation that they had, and some details regarding the training. Okay, so the base encoder network is a standard ResNet 50. The projection head was a 2-layer MLT head. And then the images were compared in 128 dimensional latent space. And although they had used a lot wider networks and a lot of things, they had a lot of ablation studies. So for further details, you can look into the paper. But as a default setting, these were the networks they used. Then the batch sizes, one of the key thing about this implementation, they have huge batch sizes. So it varied from 256 till 8192. So as you have seen before, so a batch size of 812 gives a double of its negative sample per positive pair. So because of that, they had to use a lot of memory, and in case of a GPU, and then it was the implementation had happened. And the optimizer they used, it was LARS, laser-wise adaptive rate scaling. This optimizer is used for when the batch size is way too high, and when because of these such a huge batch sizes, the gradient, the ratio of weight to gradient would be different for different layers. So with this optimizer, we have different learning rate for different layers. So that's why normal momentum and SCD may not be stable for large batch sizes. And then they use a linear warmer for 10 epochs and decay learning rate with cosine decay scheduler without restarts. which was implemented, I think, by Hutter in some of the papers. And then they used with multiple epochs, 100, 200, 400, and multiple epochs, and used a global batch normalization. So instead of normal batch normalization, they computed the statistics from all the GPUs, and then used those, averaged them, and used all those statistics with different GPUs instead of a GPU, single GPU computing its own statistic. So that was to make so that there is no leakage of information in any of the GPU. And then they used TPUs for using 32 to 128 cores and a standard data set of ImageNet. Okay, so the key findings. So they had the 4 key findings, which were the loss function, data augmentation, projection head, batch size, and epochs. So in the loss function, so they noticed that the loss benefited from the normalized embeddings and an appropriately adjusted temperature parameter. Then the data augmentation, they noticed that multiple data augmentation is crucial for defining contrastive tasks that yield effective representations. Then the projection head, a learnable nonlinear transformation between the representation and the contrastive loss, helped to get a better quality of the learned representation. Then the batch size and epochs. So contrastive learning benefits from a larger batch size and a longer training time compared to supervised counterparts. Okay, so what is contrastive loss function? So so they used a standard cost function, which is negative log of exponential similarity between one augmented view to the another augmented view divided by the parameter temperature, which is used to scale the input and widen the range of cosine similarity. And then in the denominator part, we had the image same, and then another view or the another images, the negative sample divided by tau. So this function would be explained in the next slide with the help of an example. And then what this Zj means, so it's nothing but cosine similarity, which is a normal function. So okay, intuitively what this loss function means. So we have one image. So for each image, we have like 2 augmented views, and then these 2 augmented views are put into the network. In this way, if we have a batch size of, let's say, 256, and having 2 augmentation of each image, we get a batch size of 512. That is the double of the batch size. So then they are taken one by one. A pairwise cosine similarity is calculated. So as you may see, if an image is compared with its own image, with this same augmented image, it would naturally be, the similarity would be higher. And if it's compared with another view, another augmented view of the same image, there would be still some kind of similarity within them. However, if they're compared with completely different image, probably there could be some similarity. For example, some like the background or some statistics would be same, but in overall, the number would be quite low. In this way, the whole matrix is computed, and then it's put into the log, the formula which I showed you earlier, and then the similarity takes place. We calculate again this with the negative samples, so with the whole another samples. In this way, we calculate for one loss, and then this image is flipped. And then similarly, if we calculate for this one, now we'll calculate for this, and then we get 2 loss functions. And then we make the average of both of them, and then calculate the loss function. So yeah, so that is the intuition behind the formula. Okay, so the parameters. So So while they experimenting, they found that they were like two key parameters for the loss function. So first one is the normalized embedding, another is temperature. So if no embedding is used and it has no effect, even if we change the temperature, it would have no marginal effect on the contrastive task accuracy and the top one accuracy. So what does contrastive task accuracy mean? So it is the accuracy at the latent space level. So if we have like two images which are separated apart, so it would still separate it, but if we use it for the downstream application, for example, image recognition or some object detection, so the accuracy may not be, would be different. So that is top one. So after training the network with some labels, so that is what top one means. And so if we use L2 normalization and then we change the temperature parameter, we get a different accuracy level, which you can see. Okay, so now comes the data augmentation, projection head, batch size, and epochs. So this data augmentation was one of the the most important thing that is crucial for an unsupervised learning task. So it benefits from stronger data augmentation than supervised learning. So there were some ablation studies that they uh, that took place. In that they found that even for supervised learning, we know that data augmentation do helps, but it's still not at par. No, and still not that good for getting the results. And for unsupervised learning, the accuracy would be much higher, and the accuracy would keep on increasing. So what they found that the composition of data augmentation is crucial. So instead of only using single crop or using single color distortion, the output or the accuracy of the downstream task may not be so good. So you have to have composition, two transformation or two augmentation one by one, so as to get a good um, accuracy in the downstream tasks. For example, if we look at crop and the kata, and the again a crop, we have only 33.1. But if crop is combined with color distortion, we have a good accuracy of 56.3. So in this way, they did a study for different augmentation against another augmentation. So what does single augmentation this means? So for example, they put the image and only applied the crop to one of the branch, and then it was compared with its own view at the end. But they found that this was not, it hurts the performance, and the model cannot identify it in the contrastive task. So so yeah, I mean, as you can see, they used crop resize, flip, color distortion, Sobel filtering, Gaussian blur. Although they used it for ablation studies, but for the main the results they have shown, they used random crop with flip and resize, color distortion, and Gaussian blur. And if you may think it intuitively, why random cropping and color distortion works. So it's like it encompasses two prediction tasks. So for example, if we have like cropped image, so predicting it would, if this type of augmentation is sent through the network, so we would be predicting a local view of crop A from a global view of crop B. And similarly, if we put only the D and another C is put, so it would be the task of the network would be to predict what's inside, or like how the it would look like. So it learns a representation in this form. So now comes the projection head. So as I told, so we have a nonlinear projection head, which improves the representation quality of the layer before it. So they try to use different kind of heads, a linear, non-linear, and none. So none means identity. So instead of having any network there, they would just use the output of the resonant 50. which is after the average pooling. So in this study, they found that a non-linear projection helped than a linear one. So with different dimensions, they had different top one accuracy, as you may see. So the batch size and epochs. So contrastive learning benefits from a larger batch size and a longer training time. So if we have a batch size of 256 and a lot of epochs are there, so we have this accuracy. For example, if you may look at 100 epochs and for a different batch size, the accuracy keeps on increasing. Similarly, for this, the accuracy is increasing as we have more number of epochs. So one thing that they noticed was if they go beyond 4,000, the accuracy saturates. So which does not benefits from any larger batch size or any longer training time. So, okay, so the results. So they compared the results with other self-supervised learning methods and with the supervised learning methods. So yeah, so at this time, at back then, in I think in 2020, so they had the best result and beat the state of the art, which was MoCo, and they had quite good results in their aspects. So like going apart the CPC, I think it's contrastive predictive prediction, something related, and then all the other rotation instinct tests. So all it was like the results were quite good at that period of time. And so these are the results which they compared with the other ones, and then which network they used, and the label 1% and 10%. So what does 1 and 10% mean? So after training the network, they put only 1% of the labels and trained it again. So it's like a transfer learning. And then with the 1% and 10%, so 1% of the label with with the labels, the data with the label, 1% and 10%, 10% data set with the label, and then they put. So these were the results, as you may see. And then they compared with the other supervised learning methods, which is and then on different data sets. So like foods, originally it was trained on ImageNet, and then they compared it with the other and then used for another downstream task for CIFAR 10, 100, WordSnap, and all these things. And one thing that they noticed was the self-supervised, um, the network outperformed on 5 data sets, whereas the supervised was only on 2. So and remaining 5 were almost statistically tied. So yeah, so this were the results of the SimCLR thing. And so yeah, so this concludes my small presentation, and these are the references that I used, like the papers, the blogs, and the implementations if you are interested to check them. So I think this is the fast AI thing, and then this is for PyTorch Lightning, and then this is the official release by Google Research.